Welcome to RCTech. This is Ritesh Srinivasan. In this video, I'll be explaining about clinical text classification using the Medical Transcription Kaggle Dataset. This Medical Transcription Dataset is scraped from emptysamples.com. It has anonymized sample transcriptions belonging to different medical specialties. The code is hosted on GitHub. If you are new here and like such content, please subscribe to the channel. Let's get started. Let us look at our text classification problem. Here we look at the medical transcriptions dataset from Kaggle. Here is the link for the dataset. This data was scraped from emptysamples.com. The inspiration here is that can we correctly classify the medical specialties based on the transcription text? Let us import the necessary libraries, and then we define a method to get the number of unique words in the vocabulary and the sentence count in a list of text. Now let us look at the text samples over here. So we read the CSV file, we put it into a pandas data frame, and we print the first 5 columns of the data frame. So if you look at the fields of the data frame, you have this unnamed, then you have description, then you have medical specialty, you have the sample name, you have the transcription, and you have the keywords. So the important thing for us over here in this task is, can we predict the medical specialty given a transcription text? So let's do further analysis of this data set. So let's try to group the categories of the medical specialty, and then let's see how many categories are there and how many samples are there per category. We also look at the total number of sentences in the entire transcription column and the number of unique words in the transcription column, which is your vocabulary. So let us now look at the original categories. So you have close to around 40 categories over here, and you have close to around 140k sentences in the transcription column, and the number of unique words in the transcription column is close to 35k. Right now, if you look at the categories, you have categories like allergy, autopsy, bariatrics, and you also have a lot of other categories like cardiovascular, ENT, emergency room reports, gastroenterology, endocrinology. Then you have neurosurgery, nephrology. So you have a lot of categories, and for some of the categories, you see the number of transcription records are very small. So what I did over here is I filtered out those categories which has at least more than 50 samples. Now let us look at the filtered data categories. So when I filtered the categories, the total number of categories reduces from 40 to 21. Now if you look in this particular data set, the surgery category has close to 1088 transcription records. There are also here some categories which have very less number of records, for example like emergency room reports, or for example pain management. So the number of records are quite less for these classes. Now let's look at an example for each of these class. I would not be going into each of these class, but let's look at 1 or 2 examples. So the first one category is the cardiovascular or pulmonary category. So you have this sample transcription over here which talks about a pre-operative diagnosis, which talks about post-operative diagnosis. It talks about some insertion of a right femoral triple lumen catheter. So there is some text on the transcription about the procedure and what happened during the procedure. Similarly, if you look at the consultation history and physician report, so here you have a sample transcription, a chief complaint, followed by some text description. Then you have discharge summary, again you have some transcription description. Now with this data, let me also plot the classes of this filtered data categories. So we have 20 data categories. A plot looks something like this. If you look at this plot, what becomes clear is that it is a data imbalanced problem. So because you have this class surgery, huge number of records in surgery, which is almost thrice compared to some other classes over here. So it is already a data imbalanced problem for classification. Now let us look at let us filter only the medical specialty and the transcription columns from the data set for further processing. So once we have filtered the categories of transcription and medical specialty and created a new data frame. Let us drop those rows where the transcription is not present or it is nan. So we drop that. So we get close to around 4,597 records. Then we look at some sample transcription. So if you look at some sample transcription, you see a lot of special characters. So we need to do some kind of pre-processing on this data. So for the pre-processing, we define a set of functions. One is a clean text function, which looks at punctuations and removes digits and replaces a space. So we do some pre-processing over here to clean the text and also converts it to lowercase. Then I do lemmatization on the text. So lemmatization is nothing but replacing words with similar words. So this kind of reduces the number of words present in our reduces the variability in the words. So the words which have similar meanings will get mapped to the same word. So this is the lemmatization process. So let's apply the clean method on say clean text method on the transcription data. So I lemmatize the text and I also clean the text. So after cleaning, the text looks something like this. Most of the special characters are removed and the space and other things have removed. Now let us look at how we can extract features from this data set using the Tf-idf vectorizer to generate Tf-idf features. So in information retrieval or for feature extraction, Tf-idf is a short form for term frequency inverse document frequency. It is a numerical statistic that is intended to reflect how important a word is to a document in a collection or corpus. It is also often used as a weighting factor. So the term frequency is nothing but the number of times a term appears in a document, and the inverse document frequency is nothing but the number of documents that contains a particular word. So we use this term frequency inverse document frequency as a feature extraction method over here. So we'll use this Tf-idf vectorizer, which is part of the scikit-learn package, and we use token analyzer as word level, the stop words as English, and then we say that we want to generate a Tf-idf for words, bigrams and trigrams. So that is this n-gram range over here, and we also say that if the word or bigram or trigram appears in more than 75% of the documents, then we don't consider it as a feature. We use maximum number of features, so we look at close to 1000 features over here. Then we fit the Tf-idf vectorizer on our transcription column, and if you look at some of the features or which it has captured, the Tf-idf features, it captures words like abdomen, pelvis. There is something like ABCD, which is like at a suit ABCD, basically an hospital or something. So then if you look at some of the other words over here, you have medical words over here. Now let us try to visualize the Tf-idf features using the T-sne plot. T-sne stands for T distributed stochastic neighbor embedding. It is a machine learning algorithm for visualization. So what happens over here is that it models each high dimensional object by a 2 or 3 dimensional point in such a way that similar objects are modeled by nearby points and dissimilar objects are modeled by distant points with high probability. So it is used for visualization in a low dimension space of 2 or 3 dimensions. So if you look at our feature extraction process, we extracted close to 1000 features. So from the 1000 features, we are trying to visualize it in a 2 dimension. So we create the T-sne with the 2 components, and let us look at for this 21 classes, how does the T-sne's plot look like. So if you look at the T-sne plot over here, most of the classes are quite close to each other, and the majority class of surgery kind of overlaps many other classes over here. So the data points are quite close to each other. Now let us try to actually do PCA or principal component analysis, which is to reduce the dimensionality of the features for further processing. So what we do is that we do PCA on the Tf-idf matrix. So after doing PCA, the number of features reduced from 1000 to 614. while doing PCA, we retain the components which have variance more than 0.95, so which captures more than 95% of the variance in the data set. So then we use the train test split from scikit-learn to split the data into test and train data. So we use stratified methods over here because some of the classes are minority classes. And once we do the train test split, we get the following train set is of close to 3,400 documents and a test set of close to 1,150 documents. Now on this data set, let us apply logistic regression, multi-class logistic regression to learn on the training data, to learn a classifier and to predict on the test data. So here is where we do logistic regression. So once we complete the training and we predict it on the test data set, let us visualize the confusion matrix and the classification results. So if you look at the plotted confusion matrix, which is over here, basically if the diagonal has proper values, that means the classification has taken place properly. But if you look over here, most of the data set is getting classified in this surgery class. So let us look at then so this is the predicted label and this is the true label. So this is how you get a confusion matrix plot using scikit-learn and then plotting the confusion matrix. Now if you look at the classification report over here, you will see that the overall accuracy is very low, which is 0.39. And then if you look at the bigger classes like surgery, the results are quite better. But if you look at the other minority classes, the results are really poor over here. Now let us look at what would have caused this poor results. So here is where let us apply some domain knowledge and see if we can improve the results. Now if you looked at the previous data, now if you talk about surgery, the transcriptions for surgery could belong to any of the categories, like it could be a heart surgery. So if it is heart surgery, it could belong to cardiology, but it is still present in surgery. Similarly, if it is something related to the bone, it is an orthopedic surgery, but in our data set it is present under surgery class. So what happens is that the surgery class is kind of a superset of all our other classes, right? Similarly, emergency room reports, discharge summary, consult history, office notes, SOAP chart progress, all these classes are kind of superset of certain specialty classes like cardiology, like gastroenterology, like gynecology. So what I do is that I remove these classes from our data set, and then I also remove classes like general medicine and pain management because they are also superset of our data. Now I also do some mapping of classes like neurology, neurosurgery to neurology, because neurosurgery is a branch of neurology. Similarly, nephrology and urology are related to each other. So I combine them and then I reduce the categories in our data set. So the reduced categories looks like this. So here you have close to 12 categories now. You have cardiovascular, ENT, gastroenterology, hematology, neurology. So these classes are kind of separate from each other, except that again you will see that there is radiology which kind of overlap with these classes. So now we have a total data set of close to 2324 data points. Now let us again apply some domain knowledge by using scispacy models. So these scispacy models can detect medical entities in our text. So we can use spacy. In spacy we can load this scispacy model which can detect clinical text. So again we process our data, this 12 classes of data, by using this scispacy to detect entities. So once medical entities are detected over here, we also do cleaning and lemmatization. So once medical entities are detected, the data set looks something like this. So you have the sample transcription. So you have most of the medical text extracted over here. So we have left out a lot of other text. So our features should improve over here. Now again on this data, let us do Tf-idf vectorizer. Let's get the features. Again we are collecting the top 1000 features. We use the same set of parameters as before. We again do a T-sne plot of this data set. So now on this plot you see that there are some clusters over here of data, but still this data looks a lot of overlap is still present in this data, right? So now let us again perform PCA on this data set. Then let us create train and test sets, again use logistic regression for developing a classification model, and then visualize the results. Now our train set consists of close to 1700 documents, and the test set is 581 documents. Again I am using the same logistic regression classifier. I am predicting it on the test set. Now let us look at the confusion matrix for this data after the prediction. So now if you look at the confusion matrix, you see certain classes are getting classified very well over here, which is the darker values for each of these samples. But again you see certain classes are not getting classified properly. So let us look at the overall result again. So if you look at the overall result again, you see that the accuracy over here has improved from say 0.45 or something to 0.64 over here. Again certain classes are getting classified quite well. For example, ophthalmology, because ophthalmology is very different from the other classes. But again if you see over here, certain classes like pediatrics is not getting classified properly. The class like hematology, and then you have radiology, these are not getting classified properly. So we have some improvement in the results, but we still don't have anything major improvement. Now let us look at what are the reasons for this, right? So one of the reason is that these classes have less number of values. So it's a data imbalance problem, right? So we can use something called as SMOTE, which is synthetic minority oversampling technique. So we can use this technique to generate more sample from minority class to solve the data imbalance problem. So what this method does is that it oversamples the minority classes and it undersamples the majority classes to kind of create a balanced data set. So let us generate this new data set using SMOTE. So basically this library available, it's a library available in Python called as imbalanced learn library. So from that we get the SMOTE function, and then we create our new sample. So we have created this SMOTE samples, and on these samples we do logistic regression, the same logistic regression with the same set of parameters, and let us visualize the results of the classification on the test data set. So if you look over here, it is quite similar to the earlier classification result, but then if you look at the results or the measures over here, we see that the overall accuracy has now increased to 0.67. But again there are issues with classes like radiology, with pediatrics, right? With say radiology, you have issues with pediatrics, you have issues with hematology, oncology. Now why is this happening? Let us look at the data over here. So let us look at a sample transcription from the radiology report. So what happens is that the radiology report, there are different kinds of procedures done in radiology, right? So something could be an ultrasound scan of a kidney, something could be an MRI of the brain. So lot of the keywords here will overlap with categories like neurology, it will like categories like nephrology. Similarly, if you look at pediatrics neonatal, again you will have some symptoms and other things which will overlap with the field like say neurology or cardiology or something like that. So this is the reason why we are not able to actually classify properly in this data set. So the issue over here is that the data set itself is quite noisy, that even if you try some very good classification algorithms, it is not going to give you good results. So probably something which could help over here is that we can extract some custom features for each of these classes. For example, like in radiology report, if there is a term which says radiology report, then we extract only those terms. But again the issue is that you need to sit and write custom rules to extract features from this data set, and then see if we can perform some kind of classification on this data set. So the key takeaways from this data set is that if your data set is very noisy and it is not labeled properly, then you can't do much of a classification on the data set, right? You can't really do any kind of a classification algorithm. The classification algorithm may not give you good results. The second thing is that if you have imbalanced data sets, you can look at basically the SMOTE algorithm to kind of create synthetic samples for the minority classes to improve the results. The next thing over here is that we can also look at custom feature extraction to improve the results over here. And the major thing over here is that domain knowledge plays an important role in say such classification problems. So if you have domain knowledge, for example, you know that neurology and neurosurgery are quite related to each other, you can combine and create a class. Similarly, nephrology and urology are related to each other, so you can combine that data and create a new category. Once you do like this, once you have very clearly differentiated categories over here like gastroenterology, cardiology, neurology, nephrology, then what you can do is that you can create a classification model and then you can apply the same on your surgery data to further classify the surgery as belonging to either cardiac surgery or belonging to nephrology surgery. So you can actually do it like that to improve this particular classification. And another thing over here is that if you look at the data, it is easy for a human being to put it into a certain category, because this is a discharge summary. The human is able to identify the discharge diagnosis over here and certain terms which can very clearly tell him that this is a discharge summary. But it becomes difficult for an algorithm to do the same because these keywords may not get captured properly, or you need to hand code these keywords. If you like such content, please subscribe to the channel, please like the video, please share the video, please press the bell icon so that you get notified whenever I create new videos. See you in the next video. Bye for now.